Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to this course on gas turbines and jet engines. So, today is lecture 23, which is the third lecture of the fifth week of this course. Okay. So, here in today's class we will continue the numerical examples. In the previous class we have solved one numerical design problem where we incorporated many of the aspects of real cycle. In today's problem also we will take up a practical case or practical gas turbine, which is for a multi-spool system, which we will define. I will define what it means, and we will try to analyze and find the performance characteristics by doing design point calculation for that for this system. So, similar type of problems will also be given to you in assignments. So, please practice those problems, and you should get comfortable in solving problems of this type. We are also going to give additional practice problems. So, that also you should practice, okay, and you can refer to the textbooks also, which are listed at the end of in the reference section for more problems related to this. Problem solving is one of the most important part of this course. So, as I have already explained, the concept that we will cover is how to solve numerical problem, which we will continue from the previous class, and also means as a side note we should add that we want to also get a feel for the numbers which are involved in this type of calculations. Okay. So, we will take up another problem related to industrial gas turbine. I have already mentioned the problem here. Okay. So, we have a industrial gas turbines which has two spools. What does two spools mean? So, it means that there are two shafts, okay, and the turbines. So, there are two shafts. So, two spools with two turbines, okay. Each shaft has one turbine and they are rotating separately. So, for example, if we draw schematically, so there is a shaft which connects the high pressure turbine, okay, the turbine which has high pressure gases, and this turbine runs the compressor. Anyway, this will be clear in more detail later on. Let us say that this is the compressor and this is one of the turbines. Okay. So, this is known as high pressure turbine. From the TS diagram we will see that the pressure here is higher as compared to the other turbine. Then there is a concentric shaft within the first shaft which is rotating at a different speed. So, the main advantage of having this two spool design is that both shafts can rotate at different speed. On this shaft we have a second turbine mounted. Okay. This is known as the low pressure turbine, LP turbine or low pressure turbine, and the load is mounted. Okay. So, generator or load is mounted on this low pressure turbine spool. Okay. So, the second spool. The first spool has the compressor and the high pressure turbine, and second spool has the generator and the low pressure turbine. So, this if we complete the cycle we will have a combustion chamber. So, from 01 to 02, let us use some other color. From 01 to 02 is the compression process. From 02 to 03 is the combustion. So, this is the combustion chamber. From 03 to 04 is the expansion in the high pressure turbine. Then the gas is routed back to the second turbine and it enters the second turbine at state 04 and comes out at state 5 0 5. Okay. So, exhaust gases go out at state 0 5. There are no loss, means no regenerators here and no pressure losses are given, but other types of deviations are still mentioned. So, this is the type of turbine. So, there are two spools which are both rotating with to different rotational speed. They need not rotate at different speeds, but later we will see that because the low pressure turbine size is larger, much larger than the high pressure turbine, they need to rotate at a lower speed. So, the advantage of two spool turbine is that we can design a gas turbine system with a much larger, means significantly larger low pressure turbine without dividing this gas into say two different turbines. Anyway, so it is given that the HP turbine drives the compressor like we have drawn. The LP turbine is used for power generation, and this design parameters and the other process parameters are given: ambient pressure and temperature, atmospheric pressure and 15 degree centigrade, 288 Kelvin temperature. Compressor pressure ratio is 9. Okay, remember, turbine pressure ratio need not be equal, but in this case because pressure losses are not given, we will assume negligible pressure losses. So, turbine pressure ratio also will be 9. T max, which is the turbine inlet temperature, is 1380 Kelvin. Then we have isentropic efficiency of the compressor given as 0.87. Then for both the turbine we have the same isentropic efficiency of 0.89. Because these are two different turbines, we could have had two different efficiencies depending on the manufacturing. Combustion efficiency is 99%. Calorific value of the fuel is 43,000 kilojoule per kg, and it is also given that the free turbine delivery pressure. So, the exhaust gas pressure is not atmospheric, it exhausts at a slightly higher pressure, which is equal to 120 kPa. Okay. And we need to find, based on this given data and given design. So, this is two spool system. So, based on this we need to find the performance parameters two spool gas turbine. So, we need to find the performance parameters: fuel air ratio, net specific power or net specific work output, thermal efficiency of the gas turbine and the specific fuel consumption, our standard parameters. But the problem itself is significantly different from the previous problem, although the approach intrinsically is same, that we have to find the temperature at each state and the pressure at each state, and from that the calculation for other parts follow. Okay. So, we will start by drawing a TS diagram. So, let us say that, so there are no pressure losses, no regenerator or reheat or any other types of modification. So, we have the compressor compression process going from 01 to 02. Okay. 02S is the isentropic state and 02 is the actual state. From 02 to 03 is the combustion process. Then from 03 to 04, so 4 is some intermediate pressure, we do not know, it is not stated what is pressure P04. Okay. So, from 03 to 04 is the expansion in the high pressure turbine, and from 04 to 05 is the expansion in the low pressure turbine. Okay. So, now then the cycle can be closed by going from 05 to 01 using a heat exchange process. So, the important pressure values here are the inlet pressure P01, because there are no pressure losses. Okay. So, there I have made a mistake again. Here it is given that the exit pressure from the turbine is higher than the atmospheric pressure. Okay. So, we should draw slightly differently. this will be P05, which is higher than the value of P01. P01 equal to PA because there is no velocity, okay, at the inlet. So, stagnation and static conditions are same. So, 04 to 05 will look like this. So, P01 is the inlet pressure, then we have P02 which is equal to P03, P02 equal to P03, then unknown pressure P04 and then P05, okay, which is given as 120 kPa. And this P01 is equal to 101.3 kPa. So, this is our TS diagram. So, you can see that the process from 03 to 04 is the high pressure turbine process. So, it occurs at a higher pressure, and from 04 to 05 this occurs at a lower pressure. So, this is the low pressure turbine process. Okay. So, we start solving the problem in the same way as we have done previously for all the cases. We start with going from each state one at a time. Okay. So, T01 is equal to the ambient temperature plus kinetic energy V A square by 2 Cp, which is 0. Okay. So, this is equal to Ta, which is given as 288 Kelvin. Therefore, the pressure also, because static and stagnation states are same, these are also equal. P01 is equal to Pa equal to 101.3 kPa. So, state 1 is fixed. Now, we need to find state 2. So, the pressure ratio is given. Okay. So, now this is for compressor. We will go part by part. For the compressor, it is given that P02 by P01, this is equal to RC, which is equal to 9, okay, which means that P02 is equal to, so we can obtain P02, this is equal to 911.7 kPa, because P01 is already known to us. Then T02 we have to find. So, for finding T02 we have to first find T02s. So, remember that T02s by T01, this follows isentropic relation, because this is an isentropic process. This is equal to RC to the power gamma of air minus 1 by gamma of air. So, 1.4, we have to be careful here that this is 1.4. So, if you plug in the values, you get a value of T02s with all other known values. This comes out to be equal to 539.55 Kelvin. Okay. Now, we know the next step, we know that we can now use the isentropic efficiency of the compressor to find the actual temperature or actual state of the compressor exit or compressor outlet. So, isentropic efficiency of the compressor is T02s minus 1. So, which is the ideal temperature rise by the actual temperature rise, which is T02 minus T01, okay, and this is given as 0.87. T01 we already know, which is equal to 288 Kelvin. T02s we have calculated right now, 539.55 Kelvin. So, only unknown is T02, and from here we get the value of T02 equal to 577.14 Kelvin. Okay. So, T02 and P02 are known now. Next we go to the conversion chamber. So, for the conversion chamber, let us write here. So, we are going process by process and state by state. Conversion chamber, inlet conditions are fixed. What about exit condition? P03 is known because there are no pressure losses, P03 equal to P02, which is already calculated by us, 911.7 kPa. T03 is also known. Why? Because the maximum temperature T max is given as 1380 Kelvin. Okay, so, that is the maximum temperature. So, that is what T03 is. So, this is equal to T max 1380 Kelvin. So, now we have to find the fuel air ratio from the combustion chamber calculation. Okay. So, we know that combustion efficiency multiplied by the fuel air ratio multiplied by the calorific value of the fuel. So, this is the net heat which is released. This should be equal to the energy increase in the combustion chamber, which is equal to 1 plus F Cp of gas. So, this is the energy balance T03 minus 1, mass flow rate is 1, Cp of air T02. Okay. Here remember Cp of gas is known 1.148, T03 is known 1380, T02 we have calculated, Cp of air is known 1.005, eta B is given as 0.99, calorific value is given 43,000 kilojoule per kg. So, the only unknown is the value F. Okay. So, from this calculation F comes out to be, you can write the expression for F also, Cpg. So, it is better to go in steps. Cpg T03 minus Cpa T02. Okay. This divided, so just rearranging the terms in the above equation, divided by eta B into calorific value minus Cpg T03. Okay, all the values are known, T03, T02, Cpg, Cpa and eta B. So, I am just for reference I am writing that Cpg is equal to 1.148 kilojoule per kg Kelvin. This is the value which we will use throughout the course, right. So, this comes out to be equal to 0.0245, which is again a reasonable value for a practical system, around 40:1 or slightly larger than 40:1 air fuel ratio. Okay, so, this is one of the answers. So, one question was there that what is the fuel air ratio? Fuel air ratio is 0.0245. Now, we also need to find out the net work output and efficiency, of course, also the specific fuel consumption. So, for this we want to find out the work output from the turbine. Remember that the first turbine is not generating any external work, the work which is generated by the first turbine going from 03 to 04 is fully used up just for running the compressor. So, whatever work is generated from 03 to 04 is fully used up for running the compressor. So, the net work output from the cycle is the work which is generated by the second turbine 04 to 05. This turbine is known as free turbine, okay, because this is not coupled to the compressor, this is also known as free turbine. So, the free turbine will give us the external work output. So, now we will proceed. Okay. So, let us keep this diagram again for reference. Quickly, in 1 minute we will have a reference diagram. So, again you should also practice how to draw these diagrams quickly, because it is very much essential. 01 to 02 compression, 02 to 03 combustion, then 03 to 04 high pressure turbine expansion, 04 to 05 low pressure or free turbine expansion. Okay. So, exhaust gas goes out at 05. This is P05, this is P01, this is P04 and this is P03 equal to P02. So, let us say that this is 04S and this will be this will be 05S. So, if we start with the high pressure turbine calculation for the high pressure turbine. What are known? Inlet conditions are known. T03 is 1380 Kelvin, P03 is 911.7. So, these are known. Then what we need to find? We want to find out the exit state. So, exit state temperature, is it known or pressure, is it known? So, pressure and temperature both are unknown here. Okay. So, how do we get this pressure and temperature? This is unlike the previous cases where the pressure was known, here the pressure also is unknown, we do not know, but we know that there is a given condition that the entire work generated by this turbine from 03 to 04, the entire work is used up for running the compressor. So, we can equate the work generated by the turbine is 1 plus F per unit mass flow rate, 1 plus F Cp of gas T03 minus T04. This is the work generated by the high pressure turbine per unit mass flow rate of air through the cycle or through the gas turbine. This should be equal to the work required for running the compressor, which is mass flow rate per unit mass flow rate of air, which is 1 into Cp of air into T02 minus T01. Okay. What are the unknowns here? T02 and T01 are known, right? T01 we have calculated, means we know that 288 Kelvin. T02 we have calculated 577 Kelvin. T03 is known. F we have calculated. Cp of gas is known. Cp of air is known. Only unknown is T04. Okay. So, from here we will get the value of T04 and it comes out to be equal to 1132.7 Kelvin. Please do the calculations on your own also. You can pause the calculations or pause the video and try to do the calculations on your own, because it is very important to feel confident about these calculations. The calculations are not tricky, but there are always chances of making small mistakes. So, what is the next step? Next step, of course, we want to find T05, but finding T05 is slightly tricky, because for finding T05 we want to know, we already know T04, but we also want to know the pressure ratio from 04 to 05. Now, P05 is given, but P04 is not known. So, first we have to find P04, first we have to find P04, okay, that is the next step. How will we find P04? Actual state is known, but isentropic state is not known. So, first we will find the isentropic temperature. Okay. Isentropic temperature will give us the pressure ratio, because the pressure remains same, but we can use isentropic relation. So, we know that for the turbine the efficiency in this case is defined as T03 minus T04 actual temperature difference or actual work output divided by ideal temperature difference or ideal work output T03 minus T04S. Okay. Eta T is given, eta T has been given as 0.89. and T03 we have already seen what is the value, T04 we have calculated right now. So, only unknown is T04s, so which will lead to the temperature and subsequently the pressure. So, T04s is 1102.13 Kelvin. Okay. So, now once you have T04s, we know that we can use the isentropic relation. So, T04s by T03 to the power gamma of gas, which is 1.333 divided by gamma of gas minus 1, this is equal to. So, pressure at 04s and 04 are of course same, right. So, P04 by P03 to the power. So, we have already considered the power on the other side. So, we do not need the power here. Okay. So, this is P04 by P03. Here again T04s is known, we have already calculated, and T03 is known, P03 is also known, gamma g of course is 1.333. So, only unknown is P04. So, from here we get the value of P04 and P04 comes out to be equal to 370.66 kPa. Okay. Higher, of course, it has to be higher than 120 kPa, otherwise the problem is not correctly defined. So, in this case we see that problem is correctly defined, so that we can have expansion in the next turbine. Okay. 370.66 kPa. So, state 4 is fixed. Now, we go to the final device, which is the free turbine or low pressure turbine. Okay. So, low pressure turbine. Low pressure turbine, what will we calculate? We want to calculate the work output from the low pressure turbine, okay, from 04 to 05. So, this is a standard calculation. First, we will find the value of 05s. So, T05s by T04 is equal to P05, which is 120 kPa, by P04, which is given to us, oh sorry, we have calculated right now, to the power gamma g 1.333 minus 1 by gamma g. Okay. Please take the correct value. So, from this we will get P05 we have been given 120 kPa, P04 is 370.66, gamma g is 1.333, T04 we have calculated 1132.7. So, finally, we get T05s from this, which comes out equal to 854.6 Kelvin. Okay. Now, we will use the isentropic efficiency of the turbine. So, isentropic efficiency of the free turbine is given as 0.89. So, we already know the definition. So, I am not writing, but using the isentropic efficiency we will be able to get the value of T05, which comes out to be equal to 885.18 Kelvin. So, all the states are known, pressure and temperature at all states are known. Okay. Now, we can calculate what is the net work output. Net work output is the work output from the free turbine. Okay. So, this is equal to 1 plus F, remember the mass flow rate is still 1 plus F, okay, per unit mass flow rate of air, into Cp of gas, all unknown quantity, T04 minus T05. Everything is known to us at this point. So, you will get the net work output to be equal to 291.11 kilojoule per kg. So, this is the second answer which was needed. So, this is the net specific work output from this gas turbine. So, next we need to find out the thermal efficiency. So, for thermal efficiency, I will not draw another diagram here because we can always refer to the previous one. we know that this is equal to the net work output, net specific work output by the calorific value multiplied by fuel air ratio. Okay. So, the amount of fuel required for unit mass flow rate of air. So, W net we have already calculated, which is 291.11. F also we have already calculated 0.0245, and calorific value is given to us as 43,000. So, this gives us a final value of efficiency of 0.2763. You can see that this is relatively quite low value, right, 27.60%, which means what? So, this is a realistic value for this type of gas turbine, because we have assumed all the losses, and as well as there are no additional devices here, and the temperature ranges are also not very high, and there are no regenerator to increase the efficiency. Okay. So, finally, we get the value of specific fuel consumption. So, this is another answer, and finally, we get the value of specific fuel consumption, which is equal to F by W net. This comes out to be equal to, again remember, in normal units it comes out to be a very small value, because it is per second fuel consumption is very less, kg per second per kilowatt. We convert it to per hour as we have already discussed, and this comes out to be, by multiplying by 3600, this comes out to be equal to 0.302 kg per kilowatt hour, or kg per hour per kilowatt. Okay, is a better way to write. So, the fuel required is 0.302 kg per hour for each kilowatt of power that is generated. Okay. So, this is how we solve a design problem like this. So, this was for a 2-spool turbine. Later we will see that there are various configurations of turbine. In the next class, at the beginning we will see there are 2-spool turbines, 3-spool turbines, and single spool, of course, we have seen. So, all these different configurations we will briefly discuss. Okay. So, please practice more problems like this from the textbook and from the assignments which are given to you, so that you become very familiar with the numbers which are involved and also with the calculation. Okay. So, now we conclude, we have learned in this class and in the previous class solution procedure for real gas turbines, okay, or real or practical gas turbines. Based on design calculations, we have found the performance parameters. So, in the next class, we will discuss a little bit on the performance characteristics that we can obtain by having this design point calculations repeatedly, like what we had discussed previously, and then we will move on to the next part of the course after the next class. So, these are the references. Thank you.